Hi all, welcome to Easy Max by everyone. You are learning integration. Let's see what we will cover in today's lecture. Topics that are covered in this lecture are a quick recap of previously learned concepts, solving few sums based on the direct application techniques, some standard results on integration. In our previous lecture, you have learned the definition for integration, its types, various methods that we are going to learn, and particularly you have started learning indefinite integrals and the proper definition, symbolic representation of indefinite integrals. Like integral f of x dx equal to f of x plus c, where c is called the constant of integration, and any function which is getting integrated is called as integrand. You have got introduced to this list of formulae. Let's solve few sums by using the above list of formulae. Let's solve this sum first. Evaluate integral x power 9 dx. We are going to solve this sum using this formula. Integral x power n dx equal to x power n plus 1 by n plus 1 plus c. N equal to 9 here. So, integral of x power 9 dx equal to x power 9 plus 1 divided by 9 plus 1 plus c. You should never forget writing this c. This is very, very important. So, this can be further reduced as x power 10 divided by 10 plus c. Let us take the next sum. Evaluate integral cube root of x dx. We are going to solve this sum as well using this same formula. So, let us try to get that pattern in the sum, which can be done like cube root of x can be written as x power 1 by 3, right? So, this is integral of x power 1 by 3 dx. So, you can easily say n equal to 1 by 3. So, using the formula, we have x power 1 by 3 plus 1 by 1 by 3 plus 1 plus c. So, 1 by 3 plus 1 is, taking 3 as LCM, we have equal to 4 by 3, right? So, this can be written as x power 4 by 3 divided by 4 by 3 plus c. Since the denominator goes to the numerator, this 3 will go to the numerator. So, we get 3 by 4 x power 4 by 3 plus c. This is the final answer. Let's move on to the next sum. Evaluate integral dx. So, there is no x term at all in this, right? How are we going to use this formula? We can do that. So, we can write integral dx as integral dx. Integral of 1 time dx. So, and we know one more thing. Anything power 0 is 1. So, x power 0 is also 1. So, we are going to replace this 1 with x power 0 here. So, x power 0 into dx we have. So, you can compare the given thing and the formula. So, we have n equal to 0 in here. So, using the formula, we get x power 0 plus 1 by 0 plus 1 plus c. And this can be further simplified as x by 1 plus c, which is just x plus c. Let us take the next sum. Evaluate integral 1 by x square dx. We are going to use the same formula here as well. But x is in the denominator, right? So, bring it to the numerator, which can be done using the laws of exponents, which says 1 by a power n equal to a power minus n. So, using that, we can write this as x power minus 2 dx. So you can clearly say our n is minus 2 in this sum. So using that formula, we can write this like x power minus 2 plus 1 divided by minus 2 plus 1 plus c. And this can be further simplified as x power minus 1 by minus 1 plus c. So dividing by minus 1 will change the sign of the numerator. So this will become minus x power minus 1 plus c, which can be further written as minus 1 divided by x, because x power minus 1 is 1 by x. So this is minus 1 by x plus c. And let us take the next sum. Integral 1 by 4th root of x power 3 dx. So again we are going to use the laws of exponent, which says nth root of a power m is equal to a power m to the power 1 by n. And one more rule we have, which says anything power m to the power a power m to the power n can be written as a power m times n. So using these two results, we can modify the given thing. So 1 by 4th root of x cube dx can be written as 1 divided by x power 3 to the power 1 by 4 dx. And using the next rule, we can write this like 1 by x power 3 by 4 dx. And again, we can use this result 1 by a power n equal to a power minus n here. So we get integral of x power minus 3 by 4 dx. So now we can apply the formula using n equal to minus 3 by 4. So the answer will be x power minus 3 by 4 plus 1 divided by minus 3 by 4 plus 1 plus c. So further simplifying this, we get x power 1 by 4 by 1 by 4 plus c, and denominator goes to the numerator. So this 4 will go to the numerator. 4 times x power 1 by 4, and no need to write the 1 in the denominator, plus c. And let us see the next sum. Evaluate integral 5 power x dx. We are going to use this formula here. Integral of a power x dx equal to a power x by log of a plus c. A equal to 5 here. Therefore, integral 5 power x dx is equal to 5 power x divided by log 5 plus c. Let us learn some standard results on integration. Theorem number 1 is d by dx of integral f of x dx equal to f of x. So what do you mean by this? If the given integral is differentiated again, you will get the integrand itself. Let us see how we can prove this. So let us take integral f of x dx equal to some capital F of x. And by the definition of integration, we have learned integration is the reverse process of differentiation. So when you differentiate this function, you will get the value inside. So d by dx of f of x will give you the small f of x. This by definition of integration. So let us put the value of capital F of x once again. So we get d by dx of integral f of x dx. That is how we have taken capital F of x, right? So d by dx of integral f of x dx is equal to small f of x. So when you differentiate the given integral once again with respect to x, you will get back the function inside the integral, which is the integrand. Let's learn the theorem number 2, which says integral k times f of x dx equal to k times integral f of x dx, where k is any constant. Let us see how to prove this theorem. As we have done in the previous theorem, here also we are taking integral f of x dx equal to capital F of x. Then again, by the definition of integrals, we know when you differentiate the function on the right side, you will get back the function inside the integral. That is d by dx of capital F of x will give you small f of x again. Now we want to find d by dx of k times capital F of x. We already know by the rules of differentiation, if you have a time some function of x, then you will be doing a times d by dx of f of x. So by applying the same rule here, we will be able to write this as k times d by dx of capital F of x. So this we can write as d by dx of capital F of x is small f of x. So we can write k times small f of x. And by the definition of integration, since differentiation of k times capital F of x gives you k into f of x, if we integrate this, we will get the function inside. I mean to say integral k times small f of x dx will give me this value. I mean k times capital F of x. And you know that capital F of x is integral f of x dx. So this can be further written as integral k into integral f of x dx. So we have proved that integral k times f of x dx equal to k times integral f of x dx, where k is a constant. Let us learn theorem number 3. Part 1 says integral f1 of x plus f2 of x dx equal to integral f1 of x dx plus integral f2 of x dx. Similarly, in the second part, we have integral f1 of x minus f2 of x dx. This will give you integral f1 of x dx minus integral f2 of x dx. Let's see how to prove this. Like we have taken in the previous theorems, here also we are going to take integral f1 of x dx equal to capital F1 of x and integral f2 of x dx equal to capital F2 of x. Then by the definition of integrals, we can say that when we differentiate this capital F1 of x, we will get small f1 of x. Similarly, when we differentiate this capital F2 of x, we will get small f2 of x. Now, we will try to find the differentiation of f1 of x plus f2 of x. In differentiation rules, we have learnt that d by dx of f of x plus g of x equal to d by dx of f of x plus d by dx of g of x. Using the same rule here, we can split this like d by dx of f1 of x plus d by dx of f2 of x. Again, we have kept d by dx of f1 of x equal to small f1 of x. So, this will become small f1 of x and this will become small f2 of x. So, we have obtained differentiation of capital F1 of x plus capital F2 of x equal to small f1 of x plus small f2 of x. So, by say that when we integrate the right hand side, we will get back the function inside the differentiation. I mean to say integral of f1 of x plus f2 of x dx will give me back capital F1 of x plus capital F2 of x. And of course we know capital F1 of x equal to integral F1 of x dx. So we can replace this with integral F1 of x dx and we can replace this capital F2 of x with integral F2 of x dx. So we have proved f1 of x plus f2 of x dx. This integral will give me integral f1 of x dx plus integral f2 of x dx. For proving the second part, we can just replace this plus sign over here with a negative sign. We will follow the same steps again and we will end up with integral f1 of x dx minus integral f2 of x dx. Since the proof is similar to the same thing, you can prove this on your own. In theorem 3, we have learnt two parts. One said integral f1 of x plus f2 of x dx equal to integral f1 of x dx plus integral f2 of x dx, and part 2 said integral f1 of x minus f2 of x dx equal to integral f1 of x dx minus integral f2 of x dx. These two parts can be combinedly written as f1 of x plus or minus f2 of x into dx equal to integral f1 of x dx plus or minus integral f2 of x dx. So, we can generalize this concept to n functions. Integral f1 of x plus or minus f2 of x plus or minus etc. plus or minus fn of x dx equal to integral f1 of x dx plus or minus integral f2 of x dx plus or minus etc. plus or minus integral fn of x dx. And in theorem number 2, we have learnt integral k times f of x dx equal to k times integral f of x dx. What happens if we combine this result and this result together? Generally, we can write integral k1 into f1 of x plus or minus k2 into f2 of x plus or minus etc. plus or minus kn into fn of x dx equal to k1 into integral f1 of x dx plus or minus k2 into integral f2 of x dx plus or minus etc. plus or minus kn into integral fn of x dx. Hope you understood this concept. We will start solving sums using these theorems from our next lecture. That's all for this lecture. If you find this video useful, like it and share with your friends. Stay tuned for our upcoming videos. Thanks for watching.